happening there. For example, here you see a famous example by David Toll. You know him personally, right? David, there were some function graphers internationally and in the Netherlands, VuGrafiek, and you just zoom in on a graph to notice that it is locally straight, as David Toll called it. So a graph, as soon as you are able to zoom in, resembles a line which feeds this idea of local linear approximations and tangent lines. So David Toll, once there were these graph plotters, he used it to develop this concept of locally straightness. This was in the 1980s. This was also very well known. I made it in GeoGebra, but originally it was done in Cabri or in Sketchpad. Dynamic geometry, you have properties, like in this case, perpendicular bisectors going through one point that are invariant under dragging. And I remember seeing this for the first time. I think it was in Birmingham on a conference with Michiel, if I remember well, 1991. And this was quite spectacular because this was real geometry, real mathematics in a computer. Then, of course, we had this computer algebra systems, also very spectacular because computers could do things that we considered really mathematics, real mathematics. And we always thought we are the only people, we are the only who can do that. So for example, you can have an equation and you can get square roots as answers, not just approximated values. You can have square roots with variables or with parameters as expressions. You can, well, the holy grail of algebra, the quadratic equation, it is solved by the system. I don't need to do it myself. And I can also solve it with respect to another variable, to A in this case, and then you get different type of solutions. Or, well, trig equations, which are considered very hard. So all this is embedded in the expert system, which is called computer algebra. It's also nice. A lot of work to expand x plus I to the power 10 or to factorize 100 faculty. Integration, finding antiderivatives was considered a magic art when I studied mathematics. It's no longer a magic art, it's encapsulated in the software. So these three examples, graphing, geometry, and algebra, really started to be embedded in software like 30 years ago. This was a revolution. And of course, we also had the more like pedagogically or didactically oriented tools like Peter's famous input-output algebra arrows applet. You know what it can do, I guess. It provides not only input-output relationships, but also tables, graphs. And as I said, this was quite spectacular because this is real mathematics embedded in software, whereas so far we thought we're done. Also, to prelude a bit to the rest, not so much has changed since then. These applications still form the backbone of, for example, contemporary systems like GeoGebra. Okay, and of course we had graphing calculators. So far for the tool development, what happened in class? Well, I think many people, as you could also see in the earlier examples, thought that this type of technologies could be used for concept development, better understanding, mathematical explorations by students. So I guess we all were quite optimistic about how these tools would change education for the better. On the left-hand side, you see a task that we designed for a national examination for pilot schools in the Profi project, 1999. And students were to explore how the parametric curve, which was something like the unit circle, but with some oscillation on top of it, how the number of oscillations would depend on the parameter in the parametric equation. And this was again quite new because really students used their graphing calculator to explore a new phenomenon. In teaching practices, however, some teachers felt a bit like disrupted. They had to change their practices. And this diagram shows how the type of teaching techniques that we identified in different projects, the tool use project, Peter, you were involved in it, and later the Depict one, 2013. And I'm not going to explain this in detail, but that's just to indicate that teachers were changing practices when technology entered their classrooms, even if we could clearly identify some relationships between their regular practices before that time and the new practices they developed. And the notion behind that was instrumental orchestration. So this brings me to the more theoretical developments by that time. I already mentioned this instrumental orchestration. What role do you want to play as a teacher, and how does that role change as soon as technology enters your mathematics classroom? And some teachers really still wanted to be in control of everything, like the upper one, the conductor of the symphonical orchestra. Others were more open to playing with their students with the new tools, like the jazz band player at the bottom. And this was all theoretically underpinned by Luc Trouche's idea of instrumental orchestration. Another theoretical idea that came up in that time was, this is from my own PhD thesis, the notion that when you use mathematical tools, mathematical digital tools in this case, there's always this interplay between the more technical part of how to use it, where are the buttons, what are the options, and the more mathematical part of what's my mathematical goal and how can I make the software help me achieve this goal. And for example, here is the solve command, which looks quite straightforward in a computer algebra system. But relatively young students, these were 15-year-olds, they suffer from all type of difficulties that on the one hand seem syntactical, but on the other hand have a mathematical counterpart. So for example, the need to be explicit on the variable with respect to which you solve was definitely something students struggled with. And of course I can imagine, because usually so far they've seen equations and only one variable. So it goes without saying that that's what you're going to solve to. Also, for example, the fact that a solution is no longer a number, but an algebraic expression. So while using the solve command in a computer algebra environment, we were tempted as teachers to give them some more complex equations, which led to a more advanced mathematical development in conjunction to the somewhat technical skills that they need to master. And this is the idea of instrumental genesis phrased by Michel Artigue in their 2002 paper, but already some predecessors before that. Another somewhat optimistical idea was phrased by Kathleen Hyde already, and this is a 1988 paper. That's the time that I guess Han was not even born, but still it's relevant because she said we can use technology to focus on concept development, and the more procedural skills come afterwards. That's what the resequencing means. And even if the technology by that time was far more primitive compared to now, the idea still exists. And this resonates with this overall optimism in that period on technology offering means to improve math education, to focus more on conceptual understanding. Now, does it work? Here you see some results from some review studies, meta studies. The bottom one is in fact the most recent one and the most interesting one, the Young 2017 paper. And he claims that there's an overall effect size of 0.38 reported in the studies on interventions using digital tools in math education. Of course, Arthur has warned us many times about being too simplistic on interpreting effect sizes, which of course makes completely sense. Still, my feeling is that this is a slightly positive result, and of course you should nuance it. For example, Young also reports that as soon as the studies got bigger, in terms of number of participants, the effect size decreases, which suggests that, okay, in very small scale studies, when the researcher is like very much involved, probably it's more easy to get a big effect size than when you try to disseminate it over a more bigger. So there are some nuances and some. But for the moment, my conclusion is that I'm not completely unhappy. Yes, please.
Is there a question about the slide? The number of effect sizes, does that mean the last one is a meta-meta study with 19 meta?
Yeah. So the question was, I'm going to repeat it because I'm not sure if people can hear you, what the 19 meta means, and it means that there are 19 meta studies. Yeah. What is interesting in the Young paper is also that they used this very simplistic model that we once designed, also like 15 years ago. You can use digital technology to outsource mathematics, like you want the calculator to calculate 13 times 17 for you. You could do it by hand, but you're too lazy to do so. You want to focus on something else. So you outsource it to the technology. You can use it to practice skills, these exercisers, you know them, or you can use it to develop concepts. And what you see in these effect sizes here is that, of course, concept development is the most difficult to achieve, which makes sense. So I was very pleased to see that the Young, in his meta study, used the initial 3 sections that we defined already a long time ago. Yes, please, Anna. Of pretest process or of what did you say? Or comparison to. To be honest, I forgot. I don't remember by heart. Because in fact you were asking what were the criteria that Young used to include the studies, and I'm not sure if it's always definitely pre-post or if it's also of its control included. I should. Yeah, I think it's they learned and not better than without, but I'm not 100% sure. Okay, to summarize, over the last 30 years, the development of technological tools is spectacular. Things that we now take for granted were really revolutionary a while ago. And there was a lot of optimism on the potential to pay attention to exploration and concept development. And then this instrumentation story highlighted that there's no such a clear distinction between techniques of using a tool and mathematical knowledge by the students. And also that the teacher role does matter a lot. And there were some positive effect sizes, even if you can relativate them as well. So this was the last 30 years in 30 minutes. So far, so good. Now, where are we today? And that's a mixed picture, in my opinion. On the one hand, we see old stuff reappearing. For example, we now have GeoGebra, which is very well-known software, mostly in use, I think. Very nice. If you look at the ingredients, the components, you see the regular things, the David Toll, Piet van Blokland graphing tools, the computer algebra tools as derived 20 years ago, the dynamic geometry like Cabri and Sketchpad. So in fact, it merges and improves some important things, but not essentially new, I would say. So what happened 30 years ago was really the revolution, I would say. Still, we are doing some new things. For example, here, this is a clip that many people here know already. Software that was designed by Rosa and you, Anna, maybe. I don't remember if you were involved here in Peter Bowen's GeoDefiner within the digital math environment. And what students are expected to do is, this is due, by the way, to the availability of multi-touch technology. So multi-touch technology is a new thing here. And students move one hand over the unit circle and the other on the sign graph. And if these motor actions are well coordinated, the frame gets green, and otherwise it isn't. And initially the task is as simple as try to keep the frame green. And this is supposed to be a nice sensory motor introduction to these fundamental trig properties and functions. Brief summary. So this is new technology, namely multi-touch, and new tools, in a sense, applications built in GeoDefiner. There's not much happening here. That's a bit of a disappointment. Okay, there we go. This is, of course, also Peter's work. This is the commercial break. Yeah, something's going to happen. The handwriting recognition module. I'm afraid my connection is a bit slow. Sorry? Yeah, but nothing is moving. Is it your speed? I beg your pardon?
It comes in slowly, but it doesn't move.
It doesn't?
It does move occasionally.
Yeah. It's a pity. I tried it this morning in the train, and the internet and the train was good enough. Okay, so here we see. Okay, I'm not going to wait very long, but what's happening here is the handwriting recognition, in the sense that the system only can make a mathematical formula out of your handwriting, but also in the computer algebra engine that's under the surface, so to say, under the hood, the formula is checked and evaluated. Correct me if I'm wrong, Peter. So this student will get a green tick mark in the sense that the formula is appropriate in this situation. Well, this is too slow. I'm sorry, Peter. If you want, there we go. Let's give it one chance. No, it's really slow. Okay. If I also have the film clip on my computer, but I'm not going to move to it now. But still, handwriting recognition integrated with mathematical interpretation and feedback is really very powerful and new. I will come back to it. So that's the good news. On the other hand, we had COVID emerging, and we saw that other types of tools, non-mathematical tools, all of a sudden got very important, like Zoom and Teams and so on. And what is interesting, of course, is that these tools don't have any mathematical features. So on the one hand, we see very great tools developing. On the other hand, we see what is called in literature emergency remote teaching. We see that people back to very mathematical standpoint, very primitive resources and tools. So what we saw in teaching is that teachers all of a sudden, at least 2 years ago now, moved to online teaching and struggled with that. So this is an image from our ESM paper on the practices by mathematics teachers in Flanders, Germany, and the Netherlands. And there are interesting differences, but what you see in the Netherlands is a huge amount of teachers very quickly moved to online teaching using Zoom or Teams or whatever. A lot more, for example, than in Germany. They were really lagging behind at that point. And that was interesting. The German journal Die Zeit, I don't know, picked this up and had a paper on this, which raised a lot of debate in Germany. But what we see here is that many teachers in the Netherlands and in Flanders in particular immediately moved on to distant teaching through Zoom and Teams, and had to find their ways without the regular mathematics tools. This is what they reported as well. We repeated the study 1 year later, and then, well, the Germans really caught up, so to say. They were at a similar level. What we also see is these online tutorials. In the Netherlands, you have Menno and you have Hester Vogels. You see here, internationally, at the Khan Academy. So in some sense, maybe Math D online could also be considered, or not this way?
Mention it.
Okay, I will mention it the second time in a minute. Teachers' feelings are a bit mixed. On the one hand, they can feel that, my students don't need me anymore because they all watch these videos. On the other hand, it offers some means to like flip the classroom. And sometimes these instruction videos are very instruction driven, like do this way, so very bit mechanistical. What do we have concerning more theory and research? Well, I first would like to come back. This is probably a bit difficult for you to read, but this was also from this questionnaire among teachers. And we raised 2 questions in this survey. One was what went good, and the other one was what went badly. And we have here teachers reporting. Here we have their students. And we could also connect the students' answer to the teacher answers. And we had the 3 countries. But what is interesting here, in my opinion, is that both students and teachers were more positive than we expected. For example, here you can see a large amount of teachers answering that they were quite satisfied about their teaching activity online. And we expected them to be far more negative. There were some negative here, but overall, they were, well, moderately satisfied. Also, for example, everybody always says that teachers are so upset about having limited interaction with their students when online teaching started. But if we look here at the interaction row, I have to look better. There are quite some teachers who complain about interaction. Where is it? Here. Yeah, here. There are quite some students who complain, teachers who complain, but there are also quite some teachers who report that they were quite happy with the interaction. Because if we look at their explanations, for example, they had some quite one-to-one chats during COVID times, or students could find them during like a kind of open hours. So there were the image was much more mixed. Also on formative assessments, everybody said we cannot do formative assessment. The teachers were far more positive on it than we expected. So the results from this questionnaire were more positive in my interpretation, is that it is because this was like 8 weeks or 6 to 8 weeks after school closed. And this was really a big confusion initially. And then after these 6 weeks, students and teachers found some way to deal with it. And they were a bit like relieved. Okay, it's not as bad as we expected it. So they were here quite positive. 1 year later, we have the same data. I don't have the slide yet. They were less positive and they were more nuanced, in fact, which makes sense. They noticed the limitations of this online teaching after a longer period. Going back to the more, at least in my point of view, more interesting examples of these movements with sign graph and the handwriting recognition that came through so badly. There's of course a theory about embodiments. This is Anna's paper in ESM last year, and I took the liberty to also take out a picture, Anna, which tries to depict, and correct me if I'm wrong, the interaction between, on the one hand, students' actions with some artifacts or tools, and the perceptions that they see in relation to a specific goal, aim, task, mathematical task in our case often, the body and the cognition that starts to be rooted in this interplay, in these action perception loops. Well, if you want to know more about it, speak to Anna or read the paper. I tried to make a more accessible in Dutch version. Well, this is not a version of that paper, but to write a bit on this in the new archive. Also to make sure that some, for example, mathematics community knows a bit more about it. I think this is really a very interesting direction that we are currently exploring, but that might be hindered a bit by teachers being so much concerned about their teaching in COVID period the past 2 years that, well, they might have had not that much attention to these new developments. For us as researchers, there are also interesting things here. You can go, Lonneke. Technology also offers new horizons for research. For example, this is work done by Lonneke on eye tracking technology. Anna did a lot on it. Some others did. We now can have gaze path students, which you couldn't have a decade or maybe 2 ago. And this helps us in interpreting student behavior when they watch, in this case, statistical graphs. Another example, literature research. If you now go to the university database and you Google some terms, you can cluster your literature. And this was a study we did with literature on instrumental orchestration. And we had a very skilled guy with us, and he produced this picture in 1 hour. And this would be half a year of study before we had this type of technology. So technology is not only has not only impact on math education, but also on math education research. But that's, of course, only interesting for us, not for the whole world. So, to summarize, what we see on the one hand is very interesting new tools and new approaches and new directions. For example, this notion of embodiment and instrumentation. On the other hand, we see limitations and a kind of fallback because of emergency remote teaching and COVID. And these are two things that are a bit separated and not yet completely converging, I would say. You are very silent. I hope this is a good sign. Now future, it's even more difficult, of course. And to be honest, I don't know. I don't have a completely clear view, of course. I cannot look into future, but at least we see some developments in tools. Can expect some development in teaching and in theory. And because I find it so difficult to distinguish, I put everything over the 3 boxes. One interesting thing, of course, is starting that there. Augmented and virtual reality, and that's why we put it on the front page of our Freudenthal research program. But that's just a picture. We also have some real experience with this. This was from the KEEN project in which Sylvia engaged with students who were in the praktijkopleiding, practice education for carpenter. And they had to be able to read 2-dimensional drawings of what needs to be constructed and to translate that into a 3D workplace or construction place. And they used VR glasses for that, and also the DME, the DWO, to practice with 3-dimensional perspectives. So that's one thing. What will happen in general, of course, is robots and simulations. This is not a real patient, but a robot. And what will be the impact of simulations on education? And well, of course, this is used in, for example, health education, dentist education, But will there be any applications to our field, mathematics education? I don't know. I already mentioned these classes and the impact that technology has on our own research practices. I think that's also very interesting. So how will our research techniques change thanks to digital tools? Also, of course, we have teaching practices. This was our virtual classroom at Utrecht University, but also at the Hogeschool Utrecht and many other institutes for education. We see these nice tools. For example, here Jasper has 36 screens in front of him with 36 students. He can do a lot. He can also write on these type of light boards. He can make groups. There's a lot that can be done. Very sophisticated, very advanced, not yet in a regular school, but very promising. So I think this is something we should definitely investigate. We have, of course, Veerle, who's doing her PhD on hybrid education in science and mathematics. So this is typically something that will be of interest. This is, let's see if this video is going to run. Yes, it will. Here you see 4 animations in the same time. The upper left is Anna's example of a parabola. Like you need to keep the triangle green, and you can do so through moving, it's an isosceles triangle, you can do so through moving the point over a parabola. The left one, maybe I can start it again. The left bottom one is a rectangle which has a fixed area to keep it green, so you should move a parabola, also one of Anna's example. Upper right hand side is one by Lonneke on creating histograms through visual data points. The right bottom one is by Gerben and Zohanna. That is the Fun Think project. It's for here and myself, where we try to animate nomograms. It's not moving anymore either, but you can imagine nomograms are these input-outputs. You have 2 number lines with arrows in between them. We are investigating how we can design embodied tasks using nomograms through this type of technology, which can be GeoGebra or GeoDefiner. So we have a lot of nice ideas on task design, which are to be elaborated and to be investigated. Here we have ook here once more the Wiskunde Day online, Mathematics Day online. I think using these type of light boards and these type of online courses is also something to explore. Also, as we don't know exactly how they can be accompanied, well, you had a master's student working on that recently, but how can we arrange this in a way that it's blended, maybe, that has some physical support by students or by teachers? So how to arrange this all together into fruitful and beneficial education? That's still not solved, I guess. We have digital assessments being formative or summative. There are a lot of opportunities there which still are not completely explored. And this is a mock-up of these leerdoelengrafen, the goal graphs, which Peter is working on also in the React projects. And the idea is that you have these bullets of skills and knowledge, and once you did specific tasks, you can like make one of these bullets green, and also its predecessors, like the preliminary knowledge that you need to master to be able to achieve these tasks. And then you can, so it's an oriented graph, and you can see what you've been doing well and what not, and you can imagine that you'll be redirected to your new tasks so that you know what to do next. And there are so many promising developments in this, and in the React project they are working on it. There could be artificial intelligence at the background. But if you compare this to regular practices in, for example, TIMSS or PISA, this is so much ahead of that. So there's so much work to be done to make this happen in real educational world. What you see there is sometimes so disappointing that there's really a lot of future work for us to be done. Okay, a lot of work to be done. How does digital technology impact on curricula and learning goals? That's of course a very important question, because the initial idea 30 years ago was very optimistic, like we have these tools that can do the job for us, so skip the basic skills and immediately focus on conceptual understanding and higher order mathematical thinking. This didn't work. Well, it didn't happen at least so far. And I think we really don't know what is really needed to reach these higher levels of mathematical cognition. How much by hand or how much old-fashioned practicing is needed? The easy answer, we can just skip it, seems to simplify it to me. The other way, we should continue doing all these practices, expanding brackets, because I did it when I was young, see how successful I am. That's also a very simplistic answer. So I think we really don't have exactly our fingers behind this question of what kind of skills are really needed, skills in a traditional sense, or maybe skills in a more modern sense, to reach our goals of mathematical cognition or mathematical abstraction, mathematical thinking. And as long as we don't solve this, the second question, what are basic skills, also remains open. And these two questions are very urgent at the moment now that all curricula are revised, are reformed in the Netherlands. So we have what, Peter, you're in one of these committees, or here as well. Maybe I'll get somebody. But the Ministry of Education says we need basic skills, and of course you cannot be against it. But what does it mean? What are these basic skills? Who knows online is writing a lot on this. As long as we don't have a clear view on what basic skills are, basic not in the sense of traditional, but basic in the sense of what is needed nowadays to reach for these higher levels, we have a lot of difficulties. So there's quite of a challenge. And digital technology challenges this issue. What is the importance of doing by hand equation solving or finding antiderivatives, as long as we have the tools that do it better than we can ever do it? And there was already in 1990 this paper by Buchberger, why should students learn integration rules? That's 30 years ago, and it's not solved. So we should really need to think about this. From a more researcher's perspective, the question is, of course, what new theoretical paradigms do we have? Can we use? And it's, well, I think we had this very interesting discussion on this morning. Finally, this comment by the Young Review study, 2017, namely that the observation that impact seems to get less as soon as the studies get more large scale. How can we really make sure that what we are doing in our nice offices reach practice and will be disseminated? And even if we see that studies like TIMSS and PISA do so badly sometimes in terms of type of tasks, type of skills assessed, type of technology behind, then apparently we really have difficulties in making things happen in regular education practice. But it's also something to really think about. So these are some questions that are in your graph today. There's a lot of work to do. And watch the time very clearly, but I think we are quite nicely in time, aren't we? There we are. So many different things to discuss, and I look forward to your comments. Well,
We go ahead. Share will come.
yeah, or do we have windows that can open?
Yeah, but outside.
Yeah.
That's
No, it's a sun. Okay. Maybe I stop sharing so that we can see faces.
Yes. To say something, I don't know. I didn't understand.
I can also move the laptop so maybe the microphone is more towards you.
Also to us here.
Sorry?
Yeah, exactly. Move you also to us here so that it will be a whole circle of people. Let's maybe start from the questions. And then can slowly also move to the comments and opinions and visions. Yeah.
First question. If you use a tool to replace a basic skill in education, maybe students have learned the skill at some point, but then later they don't need it. The algebra calculation. I'm really a bit surprised. Has there been no research on this? There has been. So you know a little bit about this. Can you tell something about what do you find if you start replacing basic skills for students by some system to have more focus on maybe the concepts?
Yeah.
Or higher order.
Well, I'm not sure if for sure, I don't have all the literature in my mind, but my overall opinion is that most of the studies are quite optimistic in the sense that when they try to focus, and there was also already the 1988 study by Hyde that they said, okay, we can focus more on conceptual understanding and reuse on practicing, and then once this conceptual understanding will emerge, then these by hand techniques will come relatively easily. We don't need all details, so they're quite optimistic on that. Yeah, in my opinion, most are very small scale. It never really happened large scale impact.
Because it seems a very important issue that
Yeah.
really be something.
In Australia, they have some scouts, part of their exams.
Yes.
There are experiences.
Sure. It's interesting that you refer to Victoria. I yesterday I received a paper by Dave Stacy, which was still in the embargo, and I didn't have time to read it. It's a second in this.
Because this is something for the upper secondary curriculum. Pretty important.
Yeah, you will be discussing this in your committee soon, I guess.
Basic skills.
What I would say that basic skills, I think that may be a mantra that you can use in your committee. Basic skills is not the same as traditional skills. Basic is fundamental, but what is fundamental can change over time. And due to technology, I could imagine that what's fundamental now is different from what was fundamental 100 years ago. What is fundamental now is difficult. I would like to coin this expression, the 21st century basic skills. And it sounds basic and traditional, but still it shows that it should be contemporary.
Yeah, I would like to incite also basic knowledge and basic insights. Because I think once you have your basic skills, if you taught them in the right way, they go together with some basic insight, and maybe the skill itself can more the background, something that you look up in a book.
Yeah.
I guess actually we can learn from primary education where they do both by calculating and at the end, well, we go calculate. So those two things clearly coexist. Y plus the secondary education, what coexists with the let's say the basic elementary schools in lower second.
By the way, maybe just ask, how are the people at home doing? Because we miss a meeting microphone.
I think that's very difficult to hear. Indeed.
Yeah.
But, yeah.
Can you hear anything, Michiel Kuno?
You're muted now. Yes,
It's very weak. Hard to follow.
Yeah, I'm sorry about that.
Yeah, we're really very sorry, and I'm afraid that there is not much we can do.
But the points, we are in a different building than usually, and in our own building we have these meeting microphones, but we forgot to bring one.
And
Okay.
we will try maybe to speak louder from the audience at least. And we have a question from May online. Maybe you can go ahead with your question.
Yeah, thank you very much for the presentation. I do have a question. It sort of builds on what you were just talking about with 21st century skills. And I was wondering about issues of equity. So like we are working in schools where like some students, some teachers, some educational institutions don't have the resources for technology and these advancements. I was wondering if you could speak a little bit to that, on like how we can make this available for all. If we are talking about 21st century skills, is it just for those who have the resources for this, or is it something that we can promote for everyone?
Yeah. Yeah, that's a good point, and a serious concern, of course. What I see sometimes, I'm not an expert on this. I had some experiences of countries who focus on smartphones, which seem to be quite common in many countries. So they try to design technology and interfaces that run very smoothly and very easily on smartphones. That's one way to address this. But for the rest, it is an issue and it should be taken care of. Yeah. Anybody wants to add something to that?
On one side, that can be limitations for those who can't reach, but on the other side, have the other side of the medal, because it's a kind of a way to deliver high-level designs that are normally wouldn't be available to the people around the world. So
those are the opportunities.
Yeah, so these are opportunities. So we can kind of say, yeah, we are now dreaming for the future still to come when each one will have an access. But contemporary, it is indeed only growing the difference. Yes.
Okay, that was, thank you.
If you want to comment as well, you are welcome.
No, I think like, so I really like how you set up the framework past, present, future, and then tools, teachers, and theory. And I was wondering, I guess, sort of about the students, like the recipients, where that kind of falls in. And I know they're all connected in some ways, but also I guess I tend to foreground or prioritize, like, we're talking about tools that are being created. We're talking about teachers and how they provide this instruction. But the recipients, like the effectiveness of these tools, teachers, and theories on students is something else that I guess that's sort of what prompted the whole equity question for me too, was like the role of students, like how are like the effects, the impacts of this research on students.
Yeah, good point. I forgot about students for a moment, so
Okay.
this is a joke. Yeah, no, you're right. In fact, yeah. I think I find it easier to summarize the other developments than the developments of students. Now that you say it, it's an interesting point.
Maybe the topic of technology for a student as a unique person is just to come.
Yeah.
It's not yet come. We have been so focused on how to make it efficient in general, that only now we start to think about diversity.
Okay.
Was my name mentioned?
Yes.
Okay.
You raised your hand, right?
Yeah, that's correct. I was a bit surprised that you did, first, of course, a nice overview of all those developments. It's a very long period, of course. But I was surprised that if for the future you didn't mention Konrad Wolfram, who thinks you can solve everything in mathematics education by working with computers. And I would like to hear your comment on that.
What would you like me to have said about Wolfram?
Well, he has just published the Math Fix, but earlier has these TED Talks, and his basic idea is when you use computers in education, and students figure out how to work with computers, and you have the right tasks, then they will learn to work with computers and solve all the problems that we used to solve with mathematics. So first he said we have to learn mathematics by computers. Now he says we have to learn to work with computers and replace mathematics.
Yeah. Well, you know, Kuno was my PhD supervisor, right? So you know that I'm not so much a revolutionary or a visionary person. I think I like people like Wolfram entering the debate, but in the end, I think it's a bit too it's too easy to phrase it this way, I think. Also because I believe the importance of mathematics is not only in the mathematics, it's in empowering people to organize their behavior, to organize their thinking, to structure, to see patterns. So my aim is not to avoid or to outsource mathematics to computers. In the end, my aim is to empower people to think better, so to say. And Wolfram's approach, I'm not aware of all the details of what he's been writing, but to me, sometimes it seems a bit simplistic, to be honest.
Yeah, I agree with you that I also think that he's pushing things too far. But there's still, so I don't think you can just solve everything by working on computers. But there's a balance somewhere, I think, when his claim, of course, is that they make all those computer programs like Mathematica and so forth. They have all sorts of people using their stuff, and he gets feedback from this group. And so there is some, how do you call it, compatibility between reasoning with computers and doing mathematics. And there's a trade-off. And so I think that's an interesting trade-off and a sort of balance you have to seek to find.
Yeah. What I find interesting, I'm not sure if this resonates with what you are saying, but this notion of algorithmic thinking, for example, when you want to phrase your instructions or your procedure in such a way that a computer can deal with it or that specific part of software can deal with it, that's very mathematical. And for example, we have this whole debate on computational thinking. And to me, well, again, to simplify, the intersection between computational thinking and mathematical thinking is algorithmic thinking. And algorithm also resonates to algebra. So I see some opportunities there, but just saying learn mathematics through the computer. Yeah, I'm not sure.
No, but I also think he is somewhat biased by the feedback he gets from certain groups, which are the people who are very able to do these things in let's say, industry or whatever settings. And so I'm not saying that I'm in favor of all his ideas, but I think there's a problem arising.
Thank you. Ed, I see your hand, but let's just check if there are more hands here inside. Yes, Then we will certainly have time to come back to you. Yes, Monica, but you need to shout.
Yes, so one of the interesting things about what Wolfram says is that if we take this first to primary education, it doesn't mean that you're not practicing old school skills like tables, but multiplications, I mean, but instead of applying that to abstract tasks, you should apply instead them to real life problems, like you go to the supermarket and there is a reduction of 30%. So you estimate how much 10% is and multiply it by 3. And this is something which is still a useful skill at this time. So I think this is in line with what Wolfram wants. And we need to do this kind of thinking for secondary education as well. So instead of learning only solve algebraic, quadratic equations, what is the real life use that we do today that where we could apply that so that the practice is useful when you're a citizen. And I think for the topic that I'm interested in, like statistics, there are many examples of data and data literacy where you can try to find patterns in data by graphing them and using software to graph the data, but the thinking processes you do yourself. And you do not only look for patterns in the data, but you also think about missing data, for example. So it really could be a tool to think and rethink what is needed in secondary education. And I think you also should split for students that are going to vocational education or are going to topics like psychology or sociology or that kind of topics, or the people who are in the end going to program the mathematics tools.
But in fact, what you're saying to me sounds very much like good old realistic mathematics education principles, and which, of course, for example, for VMBO, we now have this notion of functional rekenfunctional arithmetic, if I translate it literally. That, of course, makes sense, but yeah, to be honest, I don't think we need Wolfram for that.
No, but it could mean that instead of making all these formulas and trying to solve equations, you instead put them in Excel and try to figure out real life problems with that. For example, if you want to loan for buying a mobile phone, what will it cost you in the end? And program simple formulas in Excel to find that out instead of just typing it in a.
But to me, this is really RME applied to the situation that you have technology.
Yeah, but it's not yet done. Secondary education. So.
It's not maybe, not maybe completely widespread, but.
But I think that this is exactly the key question. In order to be able to think about complex situations, if we never were calculating with formulas, will kids still be able to? Yeah, so like we need some kind of, I would say, some anticipation of how mathematics work through doing by hands in order to be able to use them. So that's to me the question. Maybe we go back to Ed and then come back to the audience here.
Well, yeah, thank you. My question is about, in your speech, Paul, you were concentrating on the development in mathematics education, but then you take mathematics as an isolated subject. Well, will there not be a bigger influence of technology in make it easier to use mathematics and technology together with, for instance, physics? So shouldn't we start some integrated approaches in which we as a math teachers should work together with physics teachers, for instance, in modeling, measuring, and then you have a less isolated approach. And I think that technology makes that better possible. Do you agree with me?
Well, I think it's a very nice comment, Art. Thank you. And the topics you mentioned, like modeling, simulation, make sense to me. For some other topics or technological devices or technological resources, I find it a bit more difficult. But yeah, it's just a good point. So much to say on that. I agree with you.
Thank you.
And maybe further in general, if you have some comments and suggestions to this topic, that's also interesting. That should not necessarily be framed as a question.
Actually, are you referring at, well, just find nice application for mathematics, and physics, of course, is a nice application for mathematics. So then it's up to find more good applications for what you do. For the mathematics, as a tool.
Or maybe the other way around. You could also think of these coach-like or CMR things that starts from a physical or chemical problem situation, which of course has also mathematical aspects that emerge from it. Is that what you mean, Art?
Yes, exactly. That technology makes it better possible to take down some barriers between mathematics and other subjects, because you can get in some measurements in a computer. You can make graphs. You can I think there are all sorts of uses of technology in a physics environment that uses a lot of mathematics. So maybe technology makes it easier to get these subjects closer together.
Worthwhile trying, I would say.
Yeah. 1, 2.
Maybe in answer to, in response to Art, I find it, well, I don't understand why we don't use, for instance, a program as Coach to start modeling in mathematics classes.
Yeah.
With the graphical component in it. That makes it accessible, I think, for all students to do a little bit of modeling.
Yeah. Did you hear it, Art? So Peter was making a plea for using Coach also as a starting point for modeling.
Yeah, I agree completely with him, because what we see is that in schools these subjects are still very isolated. Mathematics teachers don't know what physics teachers do at a certain moment. They don't work together, and maybe the influence on teaching mathematics and physics is bigger in making this kind of cooperation better possible.
Thanks. Yeah, Sharon.
Thank you for your I apologize for being late, and the traffic in Utrecht is even worse than in Amsterdam. And I think You raised an interesting question of what digital skills really are. And then I was thinking, how do you teach digital skills? So what's the pedagogical content knowledge for teaching these new defined, the new definition of digital skill, basic skill? And then how do we prepare our teachers to teach the students these new basic?
Okay, these are difficult questions, Sharon. But as long as we don't know ourselves very clearly what the skills are, it's impossible to answer your questions. That's the easy answer, so to say.
Then maybe when you said that, for example, computational thinking, that the intersection with mathematics education is algorithmic thinking, maybe you can borrow some tools from computer science education to help us.
Look at Christos, who's an expert on that. Yeah, sure.
Can I speak to that?
Yeah,
On the,
yes, please do. And then Monica, if that makes sense? Or are you sharing, Anna? Sorry.
okay, so I guess I like the that was an interesting question about the digital skills, and that sort of made me wonder about like when you talk about borrowing from computer science. So like mathematical reasoning is different from other types of reasoning. But when you think about, and then computer science, I think about programming. Programming is a different type of reasoning that you do in order to like make sense of, because you're doing applications. And so I'm wondering if digital skills is actually a type of reasoning, or is it just more of a tools? Like it doesn't matter what subject is being taught. The digital skills is sort of like a user interactions with the actual tool itself that you have to learn regardless of whether it's mathematics or physics or some other subject area. But the like programming is a type of reasoning that's very different from mathematical reasoning, that's different from scientific reasoning. So yeah, I don't know. I guess maybe that was something I was wondering about and would be interested in hearing people's thoughts on that.
My thought would be that, well, the title of this talk was zooming in and zooming out. If you say, for example, programming reasoning is different from mathematical reasoning, it's maybe a bit matter of zooming in and zooming out. If you zoom out a little bit, they might have a lot in common, I think. So we can focus on the differences, and maybe we should when it comes down to details, instructional design, but we might also focus on what they have in common. I think that might also be fruitful. Right?
Thank you.
Yeah.
But then I thought also Konstantin probably could tell about computation skills.
I come back to the previous discussion about teachers cooperating with other teachers in from different topics, because I think one of the major difficulties for that is that mathematics teachers do not feel comfortable as soon as it is not about mathematics, but about science or chemistry or physics. And it's also the other way around. And some of the people here know about the study of Nathalie van der Wal, who had this research on techno-mathematical literacies at a high school, at a college. And there was the same issue, that teachers who were teaching math were not comfortable with all these other subjects. So I think if we want teachers to cooperate more or to use different topics in their mathematics classes that need, then there is a need for educational or for professional education for these teachers, or a close cooperation and teaching together, co-teaching.
Can I react? No.
Yes, I did not raise my hand, but I will provide my thoughts about computational thinking, at least in the mathematics education. Yeah. First of all, I think it was mentioned about like programming and computer science. These two are two different things. Like programming is in computer science, but it's like good not to say that like everything is about programming. I think when Paul mentioned about computational thinking and some alignments you can make with mathematics, with computer science education, programming is only one part of it. So not only that you can connect mathematics education to programming. Yeah, related with the computational thinking as a mode to connect mathematics education with, let's say, computing. I would say that it's algorithmic thinking could be, of course, be something, but maybe it's a bit misleading to only put like this direction. For example, even Wing, we produced or popularized at least computational thinking. See, something like by seeing that abstraction is like in the core of it. And we already know also with all the research that we've done that abstraction is in the heart of computational thinking, and it's like a subject for research like in mathematics education from way before that. Because also mathematics computer science education is a very new field, so it's not as mature as mathematics education. So this is a comment about computational thinking in mathematics education.
So a lot in common, but not that you already know what are the basic skills, while we do not. No, because there was this hope that maybe people from computer science know what are the basic skills, but apparently not. Basic skills, basic digital skills. And
yes, I think computational thinking is one very basic skill. Like, yeah, so we also have some language problems. I think like in that's curricula, like computational thinking is part like of digital literacy, but like to my understanding, like a linguistic point of view, digital literacy is about like only the digital meaning, but computational thinking can also be about things that are not digital. Because as the other colleagues in Denmark also mentioned, like computational thinking is not only like to make something like instead understandable like by a computer, but also an intelligent agent. This could also be like a human being. So computers can not be included in the process. So maybe this is also something that, like maybe we need to better define what is digital literacy and computational thinking. And in academic literature, there is no concrete definition, but definitely computational thinking is the way towards like a very basic skill for everyone, not only computer scientists, not only mathematicians, but something that everybody should be taught at school.
Nice. Adding complexity, that computers has nothing to, technology has nothing to do with this basic thing. Not only. Just a second, I want to make a small, Kuna, are you still, is it a new hand or an old hand? Do you have another?
It's a new hand, but it's also a new topic.
Peter and Kuna, but also I want to say a super small thing, if you don't mind. Appropriate the power here. I always wondering with the question, who does mathematics? And with this old technologies, we were so happy that computer, as you were describing, can do the formulas, and computer can turn these triangles. But now that's not a surprise anymore. And I think that's actually kind of opens up a different era when we don't want to outsource mathematics to computers and due to that benefit for the learners. And actually, I think that what we are doing now, like in our designs, is just a very different things. We are not designing, and I know we disagree here, but that's why I'm a little bit, yeah, we are not designing tools. We're designing environments. We're designing places to live and to the places that would provoke learners to do mathematics, not to do some small piece of mathematics to open up possibilities for the learners. And to me, no one better or worse. It's just really very different approaches that appear now when we are not surprised anymore by capabilities of the two.
I don't think we disagree here.
Yeah, okay. But I just thought that it might be like helpful to think about designing tools and designing environments for the students to do.
I like the word environment in this. Yeah, so, yeah. I think the word tool is sometimes more common, and I don't mind using it a bit loosely, but essentially I think I agree with you.
I think also with what I'm quite interested in is the artificial intelligence. We haven't talked so very much about it, but
there's two persons in front of you, before you.
Oh, sorry, but maybe I want to say an aspect that has not been addressed so much, that the difference between actually a person and a tool is going to be more vague in the future. Like the tool that you're working with will look a lot like a person or act a lot like a person, which sort of changes the question a little bit. Because students everyone has to work with sort of agents that represent bits of mathematics around them. It starts with the teacher. How do you relate to your teacher as a student who knows mathematics to you? Then how do you relate to your calculator? How do you relate to Wolfram Alpha that you can already pose open questions? How will you relate to an artificial intelligence that you can just ask a question? Okay, Google, what is the derivative of the sine, and how do I solve it even more? So maybe education should be generally about how you relate to some sort of entity that has some mathematics for you to use or to whatever.
Thanks for this aspect. And in the vision of time, let's just quickly also listen to Peter and then to Kuna.
One remark to Monica about what she was saying about teaching mathematics and physics. I think I'm a mathematical teacher, and I don't think I know anything about physics. And even a small teaching shouldn't change that. So I suggest we think about how to support physics and mathematics, the combination of physics and mathematics in the physics classroom. And from mathematical point, we can support that kind of reasoning about formulas, for instance, and so on. And that was the remark. My question was about your research and a lot about self-reports of teachers who were working in online platforms with their classes. And first they were very positive, then they were less positive. But when we're looking for, at this moment, back to that situation, what do we learn from that? What are the weak and what are the strong parts of it? And do you have any suggestions to analyze or, any research about
weak and strong parts of what?
The situation of online teaching?
Yeah. Can I? My impression is, but I don't have very hard evidence for that, but my impression is that teachers learn during this remote teaching during school closure. They did learn some things, and I have seen some literature on that they really take with them when going back to regular teaching, to conventional. So it seems to me that this was kind of shock, disruption, but they did learn some things that they take with them. At least that's what some teachers told in some interview studies I read. Did that answer? Is that reaction?
Well, there's the strong, maybe the strong part, and what did they take from that period, and what are the weaker points of that teaching during that period? Because there's a lot of complaining at the moment, and we see all kinds of anticipation on final exams. So some things went wrong.
You want to react there?
There is a lot of very psychological effects because they were very content the first year. It was better than they thought. After the second year, they were thinking, how long does it take? And now not so optimistic, not so satisfied anymore. And in the end, they lay back and they say, well, so and they don't have the energy to follow up on what they learned before. And maybe that's where we have to come in and try to adjust and follow up to them. What did you learn and how can we do it?
In the initial study, the teachers were quite happy and positive on their students' self-regulation skills and discipline and so. But 1 year later,
It's all months.
exactly, that's my feeling as well.
Yeah, they get tired. Kuna, could you please make the final comment?
Yeah, but it will have to be somewhat compressed. Paul, I think you were rather pessimistic about learning with computers for conceptual development. And I think there's a lot of design research showing that there is great potential there. So I would advocate for design research in this area.
Yeah, but Kuno, I completely agree with you, and I hope I was not pessimistic over it. I was pessimistic in the sense that if you look at the way in which technology nowadays is used on a wider scale, like in school books or central examinations, then you don't see much anymore from this optimism of don't see much room for exploration or concept development. It's mainly instrumental in the sense of SCAMP, instrumental like, okay, I need my calculator to calculate a normal probability or something, or an intersection point. So the ideas that emerged on the optimism on technology can contribute to concept development and exploration and so on. You don't see this back, in my opinion, in regular resources nowadays, but I still do believe there are a lot of options for it. So in that sense, I'm not pessimistic. So I think I agree with you on that.
Okay, good to hear. Thank you.
Thank you. Thank you everyone for listening and for discussion, and also for coming in person and encouraging everyone to do it twice a year this time. So thanks a lot, Paul, for this. Twice a year we will come to see each other face to face. And thanks, Paul, for the closing seminar this year.
Thank you.
So you will hear from us over September. Thanks.
Good.
Here, I mean,
You can follow me to the restaurant.
those are here on the way.
We can walk, so wherever your bike is, if there's one. Oh. Yeah.